Welcome back, everybody. Not really relevant to anything we're doing right now. I didn't go to sleep till like 1:30 last night, so I'm pretty tired because Civilization 7 is too fun. All right, so here we are, looking at things. We have a ring, a cylinder. We have, gosh, what does I represent? What about inertia? Use the whole word. The moment of inertia. Gosh, that sounds awesome, but I just don't remember what it means. Angel, we made really brief eye contact. What's a moment of inertia? Like, conceptually, what does it mean? That is correct. How hard is it to get something to start rotating, or the tendency of that object to resist a rotational force? Now, we have a lot going on here. When I did this problem initially, I didn't call it ring and cylinder. I made that note in my head that these were what I would be using. I had original and new. So, or image and pre-image, depending on how you want to think about it with whatever words. But we need a way to tie these together. So I have the force acting on what? What's that 4.5 related to? The 4.5 is? A solid wheel accelerates when a force of 4.5 Newton exerts a torque on it. So this force, I didn't label it yesterday, but it's a force that we're applying to what? If it's a wheel, what's a wheel? Cylinder. So I'm going to say sil for my shorthand. Bless you. Okay, now, Nick, you said torque. I like the idea because force and torque are kind of similar. However, if I'm just in newtons, it's very clear, I hope, that it's force. If it were a torque instead, what would the units be? Newton meters. Okay, so let's just kind of dig in and see if we can't find a relationship between some of this stuff. So we need to be able to deal with some equations. All right. I'm open to whatever. I know that I have mr squared and 1/2 mr squared, but other than that, I don't really know. I don't have the mass, so that's kind of a bummer, right? But they're the same mass, so maybe it's not. The only things that I really know that I might be able to actually use in solving are what two values for my knowns? So that's the big one, right? The force and the what? The angular acceleration, alpha. Now, as we look at this, instead of just giving it to you, I want to try to see if we can't find a way to relate angular acceleration and force, because that's what we're going to have to do. Those are the only things that we have. So right off the bat, first question, what's angular acceleration? How would we even find this? Because if I look, I don't know that there's really a force directly in the equation. But you guys will check, and you'll tell me what angular acceleration is here in a second. It's the net torque over what? Okay, so are we okay if we just say that, hey, it's torque over time? I'm going to call it delta t so I don't confuse them. Now, here's the important idea that we need to make sure that we can see here. If I'm looking at this, I have an alpha and a force that's been applied to what? The cylinder or the wheel. So as I'm looking at this, if I check it out, do you agree that this is really the torque on the cylinder? Now, if we read through the question, let's just check it. I know that this is true. I don't know how much time it took, but that's all right. If we want the same angular velocity desired, we want to exert a different force on the strap. So if I'm looking at these guys, to get to the same angular velocity for some amount of time, would we still have to accelerate at the same angular acceleration? Like, that's a mouthful, but check this out. If I weigh whatever I weigh and I want to spin a circle over 1 second, I have to accelerate 2 pi per second, essentially. I have to get up to that speed where I'm accelerating from over that amount of time from 0 to 2 pi. Everybody cool with that? Now, if I was 500 pounds instead, I would need more force to do it because I'm heavier and I have more inertia. But would I still have to rotate at the same speed? Like, I just apply more force to make myself rotate at that same rate. Which means whatever I apply to the cylinder to get it up to this, I accelerate this much, do you think it's the same acceleration that we're going to need on the ring as well? Because I still have to accelerate it from rest up to the same speed. It must be the same acceleration. The force changes, the acceleration doesn't. Does that make sense? Cool. So what could I say this is exactly equal to then? So before we get to that 3.25, let's look. This is the torque of the cylinder over time, right? And I know that this acceleration is going to have to be the same for what other object? You won't be wrong if you just give me the other object. The ring and the wheel better accelerate the same. It's the force that's different. So I know that this must be true. The torque on the ring over time is going to wind up being the same value because we need to go from rest to the same speed over the same time. Okay. This is the hardest part of this problem, recognizing this. If you don't quite understand because I'm speaking rather than writing, just notice we need to accelerate. And I'm going to say we need to have the same acceleration to get same velocity. And then you guys can be as wordy or unwordy, lack of wordless, I suppose. We need the same acceleration to get same velocity, just more force. Now, for this, we can probably reason this out realistically. We're working on setting this up. But I don't know that we really truly need to do all the fancy math, but it's really good practice. How much harder is it to spin a cylinder than a ring if they're the same mass? So it's half. So do you agree it's twice as hard to spin a ring? So we'll double check the math, but check this out. How much force did I have to spin my cylinder with? 4.5 newtons to get some amount of torque, right? Like I got torque out of it. If I have to spin a ring twice as hard because of the way moments of inertia work, how much force do you think we're going to have to put into this ring? 9 seems reasonable, right? I can see that this is my first gut instinct says, I bet it's probably 9, but we should probably verify, make sure we get practice with working with these things. So let's start knocking this out. As we go through, I think I have a typo. One little typo that I want you guys to check for me. I said that angular acceleration is torque over time. In my head, I had angular acceleration is velocity over time. If you use the resources at your disposal, can you find my mistake? Check your worksheet and the formulas. Oh my moment. It was a moment, not time in the bottom. This is an easy mistake to make, but it's an easy mistake to fix, I hope. I'm going to cross it because mistakes aren't gone. I'm just going to make sure I fix it. This is the cylinder, and this was the ring. Okay, 100%, that was an accident. I was thinking acceleration and time, didn't even bother to look at stuff. Do you guys understand why I changed it? Just straight up wrong. Okay, so these two are the same. Since these are the same, I think that we could probably solve this out. So here's what I want you guys to do. It is practice with the expanding of these things. I want you to take this equation that we have, and I'm just rewriting it so it's nice. The torque of the ring over the moment of the ring. I want you guys to find in this equation the force of the ring, which is tucked inside of one of those 4. And I want you to solve this equation for F sub r for ring after you substitute in all other known information. Now, if that is super unclear, I'm going to help us start really quickly. Torque of a cylinder. Now, I only put the cylinder there so I know what it is, right? Like, I'm not changing this. What's torque? Like, conceptually, it's rotational force, kind of, but there's a nicer formula for it. Get loud, get proud, shout it. So I heard force. That's a good start, but there's more to it. FR sine theta. Now, as we look at this, let's just think about what we really need. Do I know theta? If I'm pulling on a wheel or a gear or something, what's theta always going to be? 90, and the sine of 90 degrees is 1. Do I really need to write it? No. So the other part about this, we replace a wheel with all the mass, so we just replace this wheel with a ring, right? Now, I didn't specify it, but it's the exact same size, and I should have specified that. They're the exact same size, which means whatever the radius is, I don't know what it is. If I wanted to find the torque of the cylinder, do you agree it's just the force on the cylinder times whatever radius we're dealing with? This is how you get the torque of something. I didn't write sine theta because it's going to be 90 degrees, and I don't know what the radius is, but I know they're the same for both of them, so I'll just call it R. Okay. From this, I want you to do the same thing, expand this and this and this. And I want you to solve whatever this turns into for, what are we trying to find? F sub what? The ring. Cool. All right. I'm going to take this, move it. I'm going to let you guys do some stuff. Do me a favor. Do not plug in numbers into this yet. Don't plug in. Solve what we call the literal equation first. See if stuff divides out before you take the time to plug in numbers for them. Cool. I will give you a couple minutes to play around with the algebra, and I'll get my steps in. Cool. If you're watching this at home, go ahead and resume in 3, 2, you know what to do. As soon as we get here, remind me again real quick. What was the force that we put on the cylinder? It was 4.5 newtons. Everything is gone except 2 times 4.5 newtons equals FR, or the force that we need to exert on the hoop or the ring. We then conclude that, much to our lack of surprise maybe, we saw that you have to double your force for these moments, the way that we're looking at it. Is that what wound up happening? And we done. Cool. Okay. Looking at this, these problems can be tough to set up. I want you guys working together to knock out numbers 8 and 9. If you get both of them done and you want to check your answers, I'm cool with it. We have a lot of time left in class, but I want to have it be pretty chill for you guys. As long as we're being productive, I'm good with it. I want you to work on 8 and 9. I'll give us 10 or 15 minutes or so. We'll check them. I think I'm going to make number 10 a bonus of some sort, because 10's the hard problem. Cool. I'm going to give you guys a couple minutes. We'll get some chill tunes going. Work together, talk together. Ballarama.